Hello there, and welcome to the Sleepy Space Channel. Tonight, we are drifting slowly through the soft, luminous clouds that fill the spaces between stars, the great nebulae of the galaxy, where light travels through cold gas for thousands of years before arriving anywhere at all. These are the places where matter gathers itself into something new, where the same patient hydrogen that has drifted since the beginning of the universe quietly decides, over millions of years, to become a star. We will visit the warm, glowing nurseries of new suns, the gentle geometric shells left behind by dying ones, and the ancient cooling wreckage of stars that ended in a single brilliant moment, long before our own sun existed. 2 hours of slow, fascinating wonder, no urgency, no drama, just the soft color of light moving through the dark. You can let your shoulders soften. You can let the day grow quiet behind you. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your breathing slow. Let your eyes grow heavy. Let the day fade away. Let's begin. The Milky Way is not a fixed thing. It is not a rigid wheel of stars suspended in unchanging dark. It is something much more like a slow, layered ocean, a medium of gas and dust and light that shifts across timescales so long they become almost indistinguishable from stillness. You are inside it now, in a sense. The material that makes up every living thing on this planet was once part of that drifting medium. The air itself carries atoms that have passed through stellar interiors and returned to open space and drifted for millions of years before arriving here. The Milky Way breathes in its own unhurried way, and what it breathes is the very substance of stars. Within that slow ocean, there are regions where the medium thickens, where gas accumulates in gentle folds, where dust gathers into faint curtains, where the space between stars becomes something you might almost call weather. These regions are what astronomers have come to call nebulae. The word comes from the Latin for cloud or mist, and it is a good word. It carries the right feeling. A nebula is not a solid thing, not a body, not an object in the way that a star or a planet is an object. It is a condition, a phase of matter, a moment in the long, slow rearrangement of galactic material. There is no sound in these regions. Space is close enough to a vacuum that sound waves have nothing to travel through. The gas clouds of a stellar nursery might contain millions of times more material than our own solar system, and yet the density is so low that a human hand passing through it would feel nothing at all. The particles are simply too far apart for any wave of compression to carry from one to the next. What fills the silence instead is light. Light traveling outward from young stars, light scattered by dust grains, light emitted as excited atoms release the energy they have absorbed and send it outward as soft photons across millions of years of travel. Everything here operates on a timescale that softens urgency into irrelevance. A wisp of gas drifting outward from a dying star might take 10,000 years to travel 1 light year. A column of dense molecular gas might take 1,000,000 years to collapse into a single star. A supernova remnant might expand for 100,000 years before its edge dissolves back into the surrounding interstellar medium. These are not fast processes. They are geological in their patience. They unfold at the pace of continents, of ice ages, of deep ocean sediment. You can let yourself settle into that pace. There is no hurry here. What makes nebulae visible, what gives them the particular softness and color that fills those long exposure images, is always some form of light encounter. A bright young star nearby, illuminating surrounding gas and making it glow. A distant field of background stars, silhouetted by an intervening cloud of dust. A dying star pushing its outer layers outward into a glowing shell. A supernova's shockwave heating surrounding material until it radiates across the electromagnetic spectrum. In every case, what you are seeing is the interplay of light and matter, the way photons interact with atoms and dust grains to reveal something that would otherwise be invisible. The nebulae we will visit tonight are spread across the Milky Way, and in some cases, far beyond it. Some are close enough that their light has been traveling toward us for only a few hundred years. Others are so distant that the light now reaching us left its source before our sun had finished forming. Each one is a different chapter in the same slow story. The story of matter cycling through forms, of gas becoming stars, becoming gas again, of the galaxy rearranging itself with extraordinary patience across billions of years. You are not arriving at any of these places tonight. You are observing from a comfortable distance, the way one might watch weather move across a distant range of mountains. The clouds form and shift and dissolve, and the mountains remain, and the watching itself is a kind of rest. Let your breathing slow. Let the day behind you grow a little dimmer. The sky is not entered tonight. It is slowly noticed, already surrounding everything. A nebula is not a thing the way a rock is a thing. This is worth holding gently for a moment, because it changes how you relate to everything that follows. When astronomers speak of a nebula, they are describing a region, a place in space where the interstellar medium has taken on particular properties, where density or temperature or illumination has crossed some threshold that makes the region distinct from its surroundings. But the boundary is never sharp. The edges dissolve. The region bleeds into the medium around it. A nebula is a phase of matter, the way steam is a phase of water, recognizable, real, but not separated from the continuum it inhabits. The interstellar medium, the material that fills the spaces between stars, is mostly hydrogen. This is not surprising. Hydrogen is the original element, the one that emerged from the first few minutes of the universe's existence in the largest quantities. Helium was made alongside it in those first minutes, and helium makes up most of the rest of the interstellar medium's composition. Beyond hydrogen and helium, there are trace amounts of heavier elements: carbon, oxygen, nitrogen, iron, silicon, and dozens more, but these are minority ingredients, gifts from generations of stars that have lived and died and scattered their enriched interiors back into the surrounding space. The gas of a nebula in a young galaxy, early in cosmic history, would have been almost purely hydrogen and helium, with almost none of the heavier complexity that makes rocky planets and organic chemistry possible. Mixed in with the gas are the dust grains. These are microscopic particles, most of them far smaller than the width of a human hair, composed of silicates, carbon compounds, ices, and metallic materials. They are genuinely tiny, and yet they play an enormous role in the behavior and appearance of nebulae. Dust grains absorb and scatter light. They act like fog particles on a cosmic scale, dimming the view of whatever lies behind them and contributing to the deep opacity of the densest molecular clouds. They also act as surfaces, tiny platforms on which chemical reactions can occur, where atoms that would drift past each other in open gas can instead land, encounter each other, and bond into more complex molecules. Many of the organic molecules found in interstellar space form on the surfaces of these dust grains. The densities of nebulae vary over an enormous range, and this range matters enormously for what happens inside them. The diffuse regions of the interstellar medium, the general background of gas between stars, are extraordinarily thin by any earthly standard. A volume of interstellar gas, the size of a shoebox, might contain only a few atoms. This is far thinner than any vacuum achievable in a laboratory on Earth. But within molecular clouds, the gas thickens considerably. Dense cores within molecular clouds can reach densities millions of times higher than the surrounding medium, though they would still qualify as excellent vacuums by the standards of any Earth-based engineer. It is within these relatively dense cores that the conditions for star formation can develop, where gravity begins to exert its slow, accumulating influence on the collapsing gas. Temperature varies just as widely as density across different nebula types. The cold molecular clouds where stars form can drop to temperatures near absolute zero within just a few degrees of the lowest temperature that physics permits. These cold regions are some of the coldest places in the observable universe. At the other extreme, the gas in a supernova remnant or a highly ionized emission nebula can reach temperatures of tens of thousands of degrees. In ionized regions surrounding hot young stars, the gas is warm enough that electrons have been stripped from their atoms entirely, leaving a soup of ions and free electrons that glows softly with the light of recombination, the light emitted when electrons and ions find each other again and settle back into lower energy states. Light is the only motion most people associate with nebulae, and in a sense, this is accurate not because nothing else is moving, but because light is the only messenger that reaches us. Gas in a stellar nursery drifts, flows, and swirls, but these motions are so slow and so distant that they are imperceptible across the timescales of human observation. The light, though, is always arriving. Photons from a nebula 500 light-years away have been traveling toward us for 5 centuries. The image we see is not what the nebula looks like now. It is what it looked like 500 years ago, when those photons began their journey. In this sense, every nebula image is a portrait from the past. Many nebulae are invisible to human eyes without special conditions. A cold molecular cloud floating against the background of space has nothing to make it visible. It neither emits light nor reflects any nearby source. It is simply absence, a dimming of whatever background light might otherwise reach us. Only when such a cloud drifts in front of a bright region of background stars or glowing gas does it become visible as a dark silhouette. And yet the cloud was always there. Its invisibility was not emptiness, it was simply a lighting condition. Emission nebulae are made visible in a different way. When a hot young star or a cluster of such stars forms inside or near a cloud of hydrogen gas, the ultraviolet radiation pouring from those stars is energetic enough to ionize the surrounding gas. An ionized hydrogen atom is simply a proton, an atom that has had its single electron stripped away by the energy of incoming ultraviolet photons. When electrons and protons eventually recombine in the nebula, the electrons release their captured energy as light at specific wavelengths. The dominant color of this recombination radiation is a deep red, the characteristic glow of hydrogen alpha emission, and it is this glow that gives star-forming nebulae their characteristic warm color in long-exposure photographs. Reflection nebulae operate by a different mechanism entirely. In a reflection nebula, there is no ionization, no emission. Instead, a cloud of dust sits near a star whose light it cannot absorb efficiently. The dust scatters the starlight, and it scatters shorter wavelengths, the blue end of the spectrum, more efficiently than longer ones. The result is a nebula that glows with a cool, soft blue, borrowed entirely from the light of a nearby star. The dust is not generating anything, it is redirecting. The starlight that would otherwise continue outward in a straight line is instead scattered in multiple directions, some of it toward us, giving the cloud a faint luminosity that belongs to the star but seems to belong to the cloud. Dark nebulae absorb rather than emit or reflect. They are simply regions of dense enough dust and gas that light passing through them is attenuated significantly before reaching us. They appear dark not because they are empty, but because they are full of material that blocks the view of whatever lies behind them. Against a bright background of glowing gas or a dense field of stars, a dark nebula stands out as a region of relative darkness, a silhouette of presence rather than absence. This is worth sitting with for a moment. The dark regions in a nebula image are often the most material-rich regions, the places where matter has gathered most densely, where the conditions for star formation are most advanced, where the seeds of future solar systems quietly wait. Nebulae exist everywhere in the Milky Way and in every other galaxy. They are not rare features. They are the background state of galactic matter, the medium through which stars move, from which stars are born, into which stars eventually return. What we think of as the empty space between stars is never truly empty. It is filled with this thin, complex, layered material, sometimes illuminated and visible, sometimes dark and hidden, always present. What we see in any image of a nebula is always only a partial portrait, the portion of the structure that is currently lit, or currently silhouetted, or currently emitting. The full structure extends further in every direction, into conditions that make it invisible. The galaxy is saturated with this material. It surrounds everything. And from where we sit, inside the Milky Way, it surrounds us too, in all its quiet, invisible abundance. Somewhere in the direction of the constellation Orion, about 1,300 light-years from the place where you are lying right now, there is a cloud of gas and dust so large that it would take your eye many seconds just to scan its full extent in the night sky, if your eye were sensitive enough to see it in its entirety. Most of it is invisible. But there is a small, bright core, nestled within the sword of Orion as seen from Earth, that glows faintly even to the naked eye on a clear night. This is the Orion Nebula, and it is one of the closest large stellar nurseries to our own solar system. The Orion Nebula is a region where thousands of stars are forming simultaneously. Not one or two stars, not a quiet handful, but thousands, many of them in various stages of condensation, accretion, and early evolution. Some are fully formed young stars, still surrounded by the spinning disks of gas and dust from which planets will eventually coalesce. Some are still deeply embedded in their birth material, not yet visible in ordinary light, detectable only in infrared wavelengths that can penetrate the surrounding gas. Some are protostars, objects that have not yet begun nuclear fusion, but are collapsing under gravity, growing warmer at their cores as the infall of material compresses and heats them. At the center of the bright, visible region of the Orion Nebula sits a small cluster of very young, very hot, very massive stars. These stars are the reason the nebula glows. Their ultraviolet radiation ionizes the surrounding hydrogen gas, causing it to emit the characteristic warm glow that makes the Orion Nebula one of the most recognized objects in astrophotography. These central stars are embedded in the nebula, not floating in front of it. They are part of the cloud, having formed within it relatively recently, and now in the process of illuminating and eroding it from within. They are, in a sense, eating their own birthplace, their radiation slowly evaporating the gas that surrounded them, carving a cavity of illuminated gas and clearing a region of space that will eventually be quite empty of the material that once filled it. Around many of the young stars in the Orion Nebula, telescopes have detected small flattened disks of gas and dust, protoplanetary disks, sometimes called proplids. These are planetary systems in their earliest infancy. The disk is the raw material from which planets will form over the next several million years. The inner regions of the disk are warm, their material likely to condense into rocky bodies relatively close to the central star. The outer regions are cold, where ices can persist and where much larger, gas-rich planets may accumulate. Each of these disks is a future solar system, a possibility still in the process of deciding what it will become. Some of these disks are being eroded by the intense ultraviolet radiation from the nearby hot stars, their outer edges slowly evaporating even as planet formation attempts to proceed within them. The Orion Nebula itself is only the brightest face of a much larger structure. The Orion molecular cloud complex extends across many degrees of sky and contains far more mass than the visible nebula suggests. It is a vast reservoir of molecular hydrogen gas so cold that hydrogen atoms have paired into molecules rather than floating as individual atoms. Within this larger complex are dozens of separate star-forming regions, some active, some only beginning to condense, some so deeply embedded in dust that they are invisible to ordinary telescopes and must be studied with radio or infrared instruments that can penetrate the obscuring material. Drifting a little southward from the central bright region of the Orion Nebula, you would encounter one of the most recognized forms in all of astronomical imaging, the Horsehead Nebula. It is not a bright object. It does not glow. It is, in fact, defined entirely by what it blocks. A dense column of gas and dust rises above a glowing background of ionized hydrogen, and the upper portion of that column has been eroded by stellar winds into a shape that, from our particular vantage point, resembles the head and neck of a horse. The resemblance is a coincidence of perspective and erosion. The nebula does not know its shape. It is simply a region where material is denser than its surroundings, opaque enough to block the background glow, and partially sculpted by the radiation and wind of nearby stars. Immediately adjacent to the Horsehead, though entirely distinct in nature, is the Flame Nebula. Where the Horsehead is a dark silhouette, the Flame is a glowing emission nebula, illuminated by a very bright star in Orion's belt, whose ultraviolet output ionizes the surrounding gas and causes it to radiate. The flame appears to flicker and fold in its visual structure, an effect of the way the illuminated gas is distributed through the region, folded and compressed, and lit unevenly by the light source embedded within it. Together, the Horsehead and the Flame offer a nearly perfect illustration of the two faces of nebulae in a single field of view, the one absorbing light, the other generating it, both part of the same continuous cloud of material. Star formation in these regions occurs behind curtains of dust that ordinary light cannot penetrate. Regions that look dark and inactive in visual light images often reveal, in infrared observations, a rich population of embedded young stars and protostars, their warmth radiating outward through material that is opaque to shorter wavelengths. The Orion molecular cloud, in particular, is known to contain deeply embedded regions of star formation that remain hidden in ordinary images, detectable only through the infrared glow of warm dust and the radio emission of molecular gas. What looks like emptiness is often fullness, quietly proceeding. Turning away from Orion and moving toward the southern sky, you would find the Carina Nebula, a stellar nursery, far larger and more active than Orion's, though much less known to Northern Hemisphere observers simply because it hangs too far south to rise above the horizon for most of them. The Carina Nebula spans a region of sky more than 7 times the width of the full moon, and it contains some of the most massive and luminous stars known in the Milky Way. Among those stars is a system called Eta Carinae, an unstable and luminous object unlike most stars in the local galaxy. It is not a single star, but at least 2, one of them among the most massive objects known in our region of space. Eta Carinae has undergone dramatic changes in its brightness over the past 2 centuries of observation, though these changes are spread over decades rather than moments. In the mid-1800s, it briefly became one of the brightest stars in the sky before fading below naked eye visibility. It sits at the center of a small bipolar nebula of its own, a structure called the Homunculus Nebula, made of material ejected during past outbursts, two lobes of gas and dust expanding slowly outward in opposite directions from the central stars. This smaller structure is embedded within the larger Carina Nebula, a nested complexity of scale. The Carina Nebula as a whole is shaped by the combined radiation and stellar winds of its many massive young stars. These stars do not merely illuminate the surrounding gas, they actively push it, drive it, carve cavities within it. Stellar winds are streams of charged particles flowing outward from a star at high speeds, carrying momentum that, over long periods, can reshape large volumes of surrounding gas. The pressure of this wind compresses some regions of the nebula, potentially triggering new star formation in the compressed gas. In other regions, it erodes and disperses material, eventually clearing space around the star. The result is a nebula of extraordinary complexity, a turbulent, layered, brilliantly active region that looks, in telescopic images, like something between a landscape of eroded mountains and a vast weather system frozen at one moment of its evolution. Within the Carina Nebula, one structure in particular has attracted great attention. Mystic Mountain is the informal name given to a towering pillar of gas and dust, rising several light-years from the broader cloud below it. It is not a mountain in any geological sense. It has no solid surface, no defined mass, other than the diffuse gas and dust it is made of. But it protrudes from the surrounding nebula with a shape that is unmistakably columnar, a result of the uneven erosion of the surrounding material by stellar radiation and wind. The pillar persists because it is denser than the gas around it. While the surrounding material is blown away or ionized, the denser column resists, remaining longer before it too eventually erodes and disperses. At its tip, and perhaps within its interior, new stars are forming, triggered, possibly, by the same compression and radiation that is slowly destroying the structure around them. The Eagle Nebula, located in the constellation Serpens, contains a similar family of structures, most famously the Pillars of Creation, a set of tall, finger-like columns of molecular hydrogen gas that became one of the most iconic telescope images of the 20th century when photographed in detail. These pillars are several light-years tall. They are being eroded, slowly and continuously, by the ultraviolet radiation of a cluster of hot young stars that formed in the same cloud and now sits nearby, its radiation eating into the pillars from above. The pillars will not persist indefinitely. On astronomical timescales, they are temporary. Within them, stars are forming or attempting to form in the dense cores at the tips, where the compression from the eroding radiation may actually be encouraging gravitational collapse, even as the surrounding material is dispersed. It is a process that happens on both sides simultaneously, creation and destruction, working together, inseparable. Each pillar in the Eagle Nebula is a study in contrast. The surface facing the illuminating stars is ionized and glowing, heated and eroded by the radiation it receives. The interior is dark, cold, and dense, protected by the outer layers from the radiation that might otherwise destroy it, a region where molecular gas survives in conditions similar to the deep cores of molecular clouds elsewhere. If the pillars were sliced open, they would reveal a cold, dark interior, surrounded by a thin, bright, heated shell, like an ice cube, with its outer surface melting in warm water, while the core remains frozen. The interior is where the star formation is occurring, hidden behind the walls of gas and dust, proceeding in its own time. The Lagoon Nebula in Sagittarius is another extensive star-forming region visible to the naked eye under dark skies as a faint smudge of softly glowing light. It stretches across a region several times the width of the full moon and contains several distinct areas of active star formation within a single larger complex of gas. The name comes from a dark dust lane that runs through the middle of the brightest portion, giving the visual impression of a lagoon or channel dividing the glowing gas into two regions. This dust lane is real, a band of cooler, denser material lying in front of the glowing hydrogen behind it, absorbing some of that background light and creating a visual division that is actually a projection effect of overlapping structures at different depths. The Trifid Nebula, nearby in the same region of sky, shows the three main types of nebula in a single object, at least visually. One region glows pink-red with hydrogen emission. Another section, near a different illuminating star, glows softly blue with reflected light. And dark dust lanes divide the whole into the three lobes that give the nebula its name. The Trifid is, in this sense, a small textbook of nebula types, presenting emission, reflection, and dark absorption in a single scene. Further out, the Rosette Nebula in Monoceros demonstrates another common pattern in stellar nurseries, the formation of a large circular cavity. A young cluster of hot stars has formed at the center of a large molecular cloud, and their combined radiation and stellar winds have blown a large spherical bubble in the surrounding gas. The gas, at the edge of this bubble, is compressed by the outward pressure of the star's output, and that compression has in turn encouraged star formation in the ring of denser material at the bubble's edge. The result is a ring-shaped nebula glowing around a relatively clear central cavity, a structure that, in top-down views, looks something like a large, softly lit flower. The rosette is not exceptional in this behavior. It is, in fact, typical. Many star-forming regions show this pattern of central clearing and peripheral compression as the energy of newly formed stars shapes the material around them. There are hundreds of such regions scattered across the Milky Way, each one a unique iteration of the same general process. Some are vast complexes spanning thousands of light-years and containing millions of solar masses of material. Some are small, compact, quietly forming a single loose cluster of a few dozen stars before dispersing. They are clustered, for the most part, along the spiral arms of the galaxy, where the density of the interstellar medium is highest and the conditions for molecular cloud formation most favorable. The spiral arms are not rigid structures, but something more like slow waves of compression moving through the galactic disk. And as the disk's gas passes through these compression waves, it is encouraged to gather into the molecular clouds from which star clusters eventually emerge. Star formation, wherever it occurs, is almost never an isolated event. Stars form in groups, clusters of tens, hundreds, sometimes thousands of stars, all emerging from the same parent cloud at roughly the same time. This is because the same conditions that allow one region of a cloud to collapse tend to apply broadly across the cloud. Once collapse begins in one area, the radiation and winds of the resulting star can trigger further collapse in neighboring regions. The stellar nursery becomes self-propagating, in a sense, a wave of star formation moving slowly through the parent cloud as each new generation of stars perturbs the material around it. What results is not a single star, not a pair, but a rich cluster of stars, all born from the same cloud, carrying within their compositions the chemistry of that particular patch of galactic material. And all of this is slow. There is no rushing here. A molecular cloud may drift through space for tens of millions of years before conditions trigger significant collapse. The collapse itself, once begun, takes hundreds of thousands of years to produce a recognizable protostar. The protostar accumulates mass over another million years, before nuclear fusion ignites at its core. The surrounding nebula continues to glow and shift for millions of years after the stars within it have formed. There is time in these regions that dwarfs the entire history of human civilization and more. The nebulae we observe are midway through processes that began before our sun existed and will continue long after the light of our own star has faded from whatever records the galaxy keeps. Color in a nebula is not decoration. It is physics made visible at a distance of hundreds or thousands of light years. The specific colors that appear in nebula images are not choices made by nature for aesthetic effect. They are the direct signatures of physical and chemical processes playing out in the gas, the direct result of atoms at particular temperatures and densities releasing photons at specific wavelengths. To understand why a nebula glows red or blue or green is to understand something real about what is happening inside it. Hydrogen dominates the composition of most nebulae, and its behavior under radiation dominates their color. When a hydrogen atom in a nebula absorbs an ultraviolet photon from a nearby hot star, it may be ionized entirely, its single electron stripped away. When the electron and proton eventually recombine, the electron falls through a series of energy levels, releasing photons at each step. The transition from the third energy level to the second produces a photon with a very specific wavelength, 656 nanometers, in the deep red portion of the visible spectrum. This emission line is called hydrogen alpha, and it is responsible for the warm red-pink glow that characterizes star-forming nebulae and emission regions throughout the galaxy. When you see a nebula image dominated by red, you are seeing the light of hydrogen atoms recombining electrons and protons, finding each other again after being separated by the energy of a distant star. Oxygen contributes a different color to the spectrum of emission nebulae. Doubly ionized oxygen atoms that have had 2 electrons removed, emit strongly at wavelengths in the blue-green part of the spectrum, around 500 nanometers. This emission does not require the same intensity of radiation as hydrogen ionization, but it does require hot gas and significant ultraviolet exposure. In regions where the temperature and ionization conditions are right, oxygen emission contributes a faint blue-green component that overlays the hydrogen red, creating the complex color gradients visible in detailed nebula images. Sulfur ions contribute their own emission lines in the red and near-infrared, adding further structure to the composition of colors in highly ionized regions. Dust behaves differently from gas when it comes to light. Rather than emitting at specific wavelengths, dust scatters and absorbs light across a broad range. And it scatters short wavelengths blue light more efficiently than long wavelengths. This is exactly the same reason the daytime sky on Earth appears blue, the same Rayleigh scattering principle, operating on dust grains instead of atmospheric molecules. In a reflection nebula, where a cloud of dust is illuminated by a nearby star, the scattered light reaching us is preferentially blue, giving these nebulae their characteristic cool, soft glow. The star's original light might be yellow or white, but the reflected component reaching us through the dust is bluish, enriched in short wavelengths by the selective efficiency of the scattering. Dust also absorbs light and re-emits it at longer wavelengths. Dust grains absorb photons in the visible and ultraviolet, and the energy of those photons warms the grain slightly. The warm grain then radiates thermally, but because it is only slightly warm by stellar standards, it radiates in the infrared, at wavelengths far too long for human eyes to detect. This means that a significant portion of the energy flowing through a star-forming nebula is processed by dust and re-emitted as infrared radiation, invisible to ordinary telescopes but detectable by infrared instruments. The warm dust in a stellar nursery can be some of the brightest features in the infrared sky while appearing quite dark at visible wavelengths. The Orion Nebula, seen in infrared, reveals a completely different population of embedded objects than its visible light image, young stars and protostars that are completely hidden behind the dust when viewed at shorter wavelengths. Temperature and density together determine what kind of emission a given region of a nebula will produce. A very hot, highly ionized region near a massive young star will produce strong emission from highly ionized species, oxygen, neon, sulfur, nitrogen, each contributing its own signature wavelengths. A cooler region further from the star, where the ionizing radiation has been attenuated by distance and intervening material, will produce different emission, dominated by lower ionization states. The result, across a large nebula, is a kind of temperature map rendered in color warmer, more ionized regions glowing in different tones than cooler, partially shielded ones. The spatial variation of color in a complex nebula image is not random. It traces the temperature and ionization structure of the gas, which in turn reflects the distribution of heat sources, the geometry of the illumination, and the density variations of the material. The images of nebulae most people have seen are not what the human eye would see looking through a telescope at these objects. Long-exposure photography captures light that the eye cannot accumulate. Narrowband imaging isolates the specific wavelengths of particular emission lines, hydrogen, alpha, oxygen, sulfur, and maps them to different display colors, revealing structures that would be invisible in broadband light. When you see the classic color palette of a modern nebula image, you are looking at a representation that has been translated to a visualization of specific physical processes, color-coded for human perception. The nebula is real. The colors are real in the sense that they correspond to real wavelengths of real light. But the full richness of what is happening in a nebula extends far beyond the visible spectrum, into infrared and radio and X-ray, a layered complexity that no single image can fully represent. You can think of a nebula as a slow sound, a chord made not of vibrations in air, but of photons at different wavelengths, each one carrying information about the atom or grain that produced it. The hydrogen hum is loudest, the oxygen's contribution softer and cooler, the sulfur's a faint low note underneath. Together they compose a spectrum, and from that spectrum, careful interpretation can extract temperature, density, velocity, composition, and age. The nebula is legible in its own quiet way. It speaks through light at every wavelength, and what it says is a long, patient account of its own physics. There is a particular kind of quiet in the way a sun-like star ends. It does not collapse dramatically. It does not explode. It does something gentler and, in its own way, more intimate. It exhales. Over thousands and then tens of thousands of years, it releases its outer layers into the surrounding space, expanding and thinning and drifting outward until what remains at the center is a small, hot, dense remnant no larger than Earth. The compressed core of what was once a star, quietly radiating the last of its stored heat into the long dark. The outer layers, meanwhile, drift outward in a slowly expanding shell. They are thin, far thinner than any atmosphere, far thinner than the gas of a stellar nursery. But the hot remnant core at the center, called a white dwarf, radiates intensely in the ultraviolet, and that radiation ionizes the surrounding expanding gas. The shell begins to glow. The colors and patterns that emerge from this glow depend on the composition and geometry of the expelled material, on the presence of magnetic fields and rotation, on whether the central star has a companion whose gravity distorted the manner of the mass loss. Each planetary nebula is unique in its details, but all of them share this fundamental structure, a hot, compact remnant, surrounded by a glowing shell of its own former atmosphere. The name planetary nebula is a historical accident. Early observers looking through small telescopes noticed that some of these objects appeared as small, round, colored disks, faintly reminiscent of the disk of a planet Uranus. Newly discovered and of modest apparent size, seemed to these observers to offer a useful comparison. The name stuck, even though planetary nebulae have nothing to do with planets in any physical sense. They are not related to planetary formation. They are simply the glowing shells of expelled stellar material, encountered at a particular phase of their expansion, when they appear as relatively small, roughly circular structures against the background of stars. The formation process begins long before the nebula itself appears. A star like the Sun spends most of its life fusing hydrogen into helium at its core, a stable and unhurried process that can continue for billions of years. But when the hydrogen in the core is exhausted, the star's structure changes. The core contracts and heats. While the outer layers expand greatly, the star swells into a red giant, many times larger than before, cooler at the surface, but far more luminous overall. At this stage, the star begins losing mass more rapidly, driven by stellar winds strengthened by the large, loosely bound outer envelope. The mass loss at this stage is slow, not a sudden shedding, but a continuous gentle wind carrying material outward over millions of years. As the star continues to evolve, the mass loss can accelerate significantly. In the final stages of a red giant's evolution, the star may lose mass in episodic pulses, multiple shell ejections over thousands of years, each one adding a layer to the expanding outward envelope of material. The result, in the surrounding space, is a complex layered structure of shells, each one representing a different episode of mass loss, each one expanding at a slightly different speed from the ones around it. These multiple shells, glowing and interacting, contribute to the intricate onion-like structure seen in many planetary nebulae when imaged in detail. The Ring Nebula in the constellation Lyra is perhaps the most immediately recognizable planetary nebula to Northern Hemisphere observers. It appears as a soft, elliptical ring of glowing gas, warm in color at its inner edge and fading toward blue further out. The ring is not a flat disk, it is a three-dimensional structure, more like the surface of a barrel or a cylinder viewed end-on, with the white dwarf at the center. What appears as a ring is the projection of this roughly tubular structure onto the plane of the sky. The central star is faint but detectable in deep images. A small hot point of light at the geometric center, the source of the ultraviolet radiation that keeps the surrounding shell aglow. Over time, the shell will continue to expand, growing larger and thinner and fainter, until it dissolves back into the surrounding interstellar medium, its atoms mixed into the general diffuse gas of the galaxy. The Helix Nebula in Aquarius is one of the nearest examples of a planetary nebula. Its proximity makes it one of the largest in apparent size. It spans a region of sky roughly 3 times the apparent width of the full moon, but it is too faint for the eye to detect without a telescope. In long exposure images, it presents as a series of concentric, layered rings, giving an impression of depth and structure that suggests multiple episodes of mass loss from the central star. The innermost regions glow more intensely, ionized most strongly by the nearby white dwarf. The outer regions are fainter, cooler, less ionized, the earlier, more distant shells of material. There is something almost like a geology to the Helix Nebula, a stratigraphy of stellar history, written in glowing gas at distances of hundreds to thousands of astronomical units from the remnant core. The Cat's Eye Nebula, in Draco, takes this complexity further. It shows nested shells, elongated structures, and complex inner patterns suggesting a long history of mass loss events and possibly the influence of a binary companion on the dying star's geometry. It is one of the most structurally complex planetary nebulae known, a testimony to the complicated ways that stellar death can unfold when the initial conditions are not simple. The central star, whatever the nature of the system surrounding it, left behind a record of its last centuries in the expanding gas, a record we can still read in the shapes of the shells. Bipolar planetary nebulae present a more dramatic geometry. Instead of roughly spherical or ring-like structures, these nebulae expand preferentially along one axis, forming two lobes or wings extending in opposite directions from the central star. The Butterfly Nebula, also called the Bug Nebula, in Scorpius, shows this two-winged structure clearly, two large, luminous lobes separated by a dense equatorial band of material that is thicker and slower moving than the polar outflows. The two lobes expand at much higher speed than the equatorial material. This asymmetry in the outflow creates the pinched, winged shape. The asymmetry itself is thought to result from the rotation of the central star or binary system, with equatorial material concentrated by centrifugal forces, while the poles eject material more freely. The Ant Nebula shows an even more elongated structure, a narrow, jet-like form, suggesting that the mass loss was highly directed, channeled by magnetic fields or the gravitational influence of a companion into two opposing jets rather than a general spherical wind. Bipolar structures in planetary nebulae are thought to be associated more often with binary central star systems, where the presence of a companion influences the geometry of the mass loss and shapes the expanding nebula. Binary interactions during the final phases of stellar evolution can transfer mass, alter rotation rates, and create conditions that strongly prefer outflow in particular directions over others. All planetary nebulae are temporary structures. Their gas is expanding outward at speeds of tens of kilometers per second, which sounds fast by everyday standards, but across the vast distances of space means that even over tens of thousands of years, the nebula grows by only a small fraction of a light year. Eventually, after perhaps 20,000 or 50,000 years of expansion, the shell has grown too large and too thin to be ionized efficiently by the fading white dwarf, whose ultraviolet output diminishes as it cools. The nebula fades. Its gas mixes with the surrounding interstellar medium. The white dwarf continues to cool slowly over billions of years, an ember gradually dimming, preserving within its compressed mass the nuclear ashes of its stellar life. The material released by planetary nebulae is not lost. It is enriched. The outer layers of a sun-like star, processed through billions of years of nuclear burning and dredged up by the convective mixing of the red giant phase, contain significant quantities of carbon, nitrogen, and other elements synthesized during the star's life. When these layers are expelled, they carry those elements into the interstellar medium, enriching it gradually over time. The galaxy, after billions of years of stellar evolution, is chemically richer than it was at the beginning, more complex, more varied, more capable of supporting the chemistry of planets and life. Planetary nebulae are among the processes responsible for this enrichment. The carbon in organic molecules throughout the galaxy owes part of its origin to stars that died this way, gently, in expanding colored shells, and scattered their interiors into the surrounding space. When a star is massive enough, its ending is quite different from the slow exhalation of a sun-like object. A massive star, 10, 20, 30, or more times the mass of the Sun, burns its fuel with an urgency proportional to its mass. It lives fast, and it ends suddenly, in a collapse that releases more energy in a few moments than the Sun will emit across its entire 10 billion-year lifetime. What remains after this collapse is either a neutron star, a city-sized ball of matter, so dense that a teaspoon of it would outweigh a mountain or a black hole, the collapsed remnant too dense for anything to leave. And the outer layers of the star, expelled in the shockwave of the collapse, expand outward at enormous speeds into the surrounding interstellar medium, heating and compressing the gas they encounter, and creating a structure that will continue expanding and evolving for hundreds of thousands of years. These structures are supernova remnants, and they are among the most energetic and complex objects the galaxy produces. The initial expansion is incredibly rapid. The shock wave from a supernova can reach a significant fraction of a percent of the speed of light in its early stages. This shock wave heats the gas ahead of it to millions of degrees, creating a bubble of extremely hot, tenuous plasma surrounded by a compressed shell of swept-up interstellar material. This hot interior radiates in X-ray wavelengths the signature of gas at temperatures far beyond anything ordinary emission nebulae produce. The expanding shell, as it sweeps up more and more surrounding gas, slows. What began as a violent and rapid expansion gradually decelerates over thousands of years into a slower, larger, more diffuse structure. The Crab Nebula in Taurus is one of the best-studied supernova remnants in the sky and one of the youngest visible ones. Historical records describe the appearance of a new bright star in this region of sky roughly 1,000 years ago, bright enough to be seen in daylight for several weeks. That star was the light of a supernova, the death of a massive star that had already been burning for millions of years before its collapse. What those observers saw was the initial burst of light from the explosion. The nebula we see today is the expanding debris from that event, a complex, luminous, filamentary structure filling a region several light-years across. At the center of the Crab Nebula sits a pulsar, a neutron star, rotating about 30 times per second and emitting beams of radiation from its magnetic poles as it spins. The pulsar is not merely the remnant of the explosion, it is an active engine, pumping energy into the surrounding nebula through a wind of relativistic particles. This pulsar-wind nebula glows in X-rays and optical light in a way that is qualitatively different from the outer filaments. It is powered not by thermal emission from hot gas, but by synchrotron radiation, the light emitted by electrons moving at close to the speed of light in the pulsar's magnetic field. The result is a complex, layered structure in which the inner regions glow with the energy of the spinning pulsar, while the outer filaments are the remnants of the star's original outer layers, still expanding outward from the site of the explosion. The Veil Nebula, in Cygnus, represents a very different phase of supernova remnant evolution. It is old. The explosion that created it occurred perhaps 8,000 years ago or more, and the expanding shock has spread across a large region of sky, becoming extremely thin and delicate in appearance. What makes the Veil Nebula so visually distinctive is the way the cooling gas has organized into long, flowing filaments, sheets, and wisps of glowing material that appear almost like curtains of light against the background star field. The gas in these filaments has cooled enough that it no longer emits primarily in X-rays, but in the visible emission lines of hydrogen and oxygen, making it detectable in narrowband imaging at wavelengths the eye can register. The filamentary structure arises from the instabilities that develop as the shock-heated gas cools and the interface between the hot interior and the surrounding interstellar medium becomes wrinkled and folded. Cassiopeia A is a supernova remnant, so young by astronomical standards that it can almost be called fresh. The explosion that created it is estimated to have occurred in the 17th century, though the light apparently reached Earth without being widely recorded by observers. In the centuries since, the remnant has been expanding, and it now appears as a roughly circular shell of extremely hot gas glowing intensely in X-ray wavelengths. Within its expanding shell are dense knots of material, the original outer layers of the star, expelled in the explosion, now moving outward at thousands of kilometers per second. These knots are enriched with the heavy elements that the star synthesized during its lifetime: oxygen, silicon, sulfur, calcium, iron elements that will eventually mix with the surrounding interstellar medium and become available for incorporation into future stars and planets. The Vela supernova remnant in the constellation Vela is another ancient remnant, sprawling across an enormous area of sky and centered on a pulsar, the compressed remnant of the star's core, now spinning about 11 times per second and emitting regular pulses of radiation. The remnant itself is a complex tangle of filaments and partial shells, overlapping with other supernova remnants and regions of emission nebulosity in a region of sky rich with the aftermath of multiple stellar explosions. Vela offers a view of what happens on very long timescales after hundreds of thousands of years of expansion. A supernova remnant has become so large and so diffuse that it merges gradually with the general interstellar medium, its energy dispersed, its boundaries dissolved. SN 1987A, a supernova, observed in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, in the year 1987, has provided an extraordinary opportunity to watch a supernova remnant form in near real time. Over the decades since the explosion, the expanding debris has been monitored as it collides with rings of gas that were shed by the progenitor star in its final centuries before the explosion. These rings, pre-existing structures that date from an earlier phase of the star's evolution, are now being struck by the shockwave from the supernova and have lit up brilliantly in response. The collision points are expanding and brightening over the years, forming an arc of hotspots around the inner ring, a process that can be watched unfolding on a human timescale, a remarkable compression of astronomical time into observational experience. The chemical contribution of supernovae to the galaxy is perhaps their most significant long-term legacy. The heaviest elements in the periodic table, iron, nickel, gold, platinum, uranium, are synthesized in the extreme conditions of a massive star's interior and the violent moments of its collapse and explosion. These elements would remain locked inside the star were it not for the explosion that disperses the star's material across light years of surrounding space. Every atom of iron in your blood was once inside a star. Every atom of gold anywhere on Earth was forged in conditions of extraordinary energy, a stellar death, and then scattered into the cloud from which the solar system formed. Supernova remnants are not simply beautiful, they are the distribution network of the galaxy's chemistry. The means by which the heavy elements synthesized in stellar interiors eventually reach the broader interstellar medium and become available for incorporation into future generations of stars, planets, and everything that might inhabit them. As remnants age, they change. The hot interior plasma cools over tens of thousands of years. The expanding shell interacts with the increasingly dense and irregular interstellar medium, developing instabilities that break the initially smooth circular or spherical shape into complex asymmetric structures. The energy input from the central pulsar, if one exists, maintains a bright inner component while the outer shell fades. Eventually, after 100,000 years or more, the remnant has dispersed sufficiently that its edges are indistinguishable from the surrounding medium. Its energy has been transferred. Its material has been mixed. Its contribution to the chemical enrichment of the galaxy has been delivered. The space it occupied has returned to the general condition of the interstellar medium, slightly enriched, slightly heated, waiting for the next cycle of condensation and star formation to begin. There is a kind of presence that reveals itself only through absence. A dark nebula does not glow. It does not emit radiation of its own in any wavelength easily seen by the eye. It is defined by what it blocks the background starlight or glowing gas that cannot penetrate the densely packed dust and molecular gas of which it is made. And yet a dark nebula is not empty space. It is, in fact, among the most densely material-rich regions in the interstellar medium. What looks like a gap or a hole in the star field is actually a concentration of matter, a region where gas and dust have accumulated to a density sufficient to stop light in its tracks. The most visually prominent dark nebula structure in the night sky is the Great Rift, the dark lane that appears to divide the Milky Way in two across a large arc of sky, particularly prominent in summer skies from the northern hemisphere. This rift is not a gap in the galaxy's stars. It is a dense region of molecular clouds lying between us and the more distant star fields of the galactic center, close enough and thick enough to absorb most of the visible light from the stars beyond. The stars behind it are real, they shine. Their light simply cannot reach us through the intervening dust. The Great Rift is a structural feature of our local region of the galaxy, a band of molecular cloud complexes running along the spiral arm in which the solar system is embedded. Within the broader category of dark nebulae are objects of many different scales. The largest dark clouds, the giant molecular clouds, can contain millions of solar masses of material and stretch for hundreds of light years. These are the ultimate reservoirs of star-forming material, the raw stock from which entire star clusters and associations will eventually condense. They are cold. Temperatures within them can drop to 10 or 15 degrees above absolute zero, conditions so cold that many molecules that would be unstable at warmer temperatures can survive and persist. At these temperatures, hydrogen has long since paired into molecular form. Other molecules, water, carbon monoxide, formaldehyde, even complex organic molecules form on and around the surfaces of the embedded dust grains and drift through the cold gas in low concentrations that are nevertheless detectable in radio observations. At the smaller end of the scale are structures called Bok globules, compact, roughly spherical dark clouds that stand out against bright emission nebulae or star fields as distinctly dark, isolated spots. These objects range from a fraction of a light-year to a few light-years in diameter, and they typically contain a few solar masses of material. Many Bok globules are in the process of collapsing towards star formation. Their central densities are high enough, their temperatures low enough, that gravity is gradually winning against the thermal pressure of the gas. In some cases, infrared observations have revealed embedded protostars within Bok globules, the very early stages of new stars forming within these small, quiet, self-contained patches of darkness. The Horsehead Nebula, discussed earlier in the context of Orion's star-forming regions, is a prominent dark nebula. Its recognizable shape is a section of a larger dark molecular cloud, the lower portion of which is illuminated from within by a young embedded star that makes the background glow, while the dense upper portion of the cloud, not yet eaten through by radiation, remains dark and opaque against the glowing background. The three-dimensional structure of the Horsehead is likely more complex than the familiar silhouette suggests. The nebula is not a simple pillar, but a section of a folded, irregular cloud whose overall geometry we see only partially projected onto the sky. The Pipe Nebula, in Ophiuchus, is a large, dark nebula complex that takes its name from the overall shape traced by its dark lanes against the star field of the central Milky Way. Unlike the more dynamic dark nebulae near active star-forming regions, the Pipe Nebula appears to be in a relatively early stage of evolution. Its material is not yet strongly collapsing, though it contains several dense cores that may eventually form stars. It is cold, quiet, and enormously massive for its apparent simplicity. Radio observations show that the gas within it has very little internal turbulence, a calm, cold reservoir of molecular material, waiting for some perturbation to nudge it toward collapse. The chemistry of dark nebulae is remarkable for its complexity, given the conditions involved. Cold, dense, shielded from ultraviolet radiation by the dust that surrounds them, the interiors of these clouds are chemical laboratories of a particular kind. Molecules that would be quickly destroyed in the ultraviolet-exposed interstellar medium survive within the shielded interiors of dark nebulae. Dust-grained surfaces act as catalysts, allowing atoms to meet and react that would never encounter each other in the thin gas alone. Over millions of years of exposure to the low-energy conditions inside a cold cloud, this surface chemistry builds up increasingly complex molecular species. Amino acids, sugars, alcohols. These and simpler precursor molecules have been detected in the interstellar medium and in the cold gas associated with molecular clouds, suggesting that the raw ingredients for organic chemistry are distributed widely through the galaxy. Temperature in a dark nebula controls much of its behavior. At 10 to 20 degrees above absolute zero, the thermal energy of the gas is very low, too low in most cases, to support the gas against gravitational collapse without additional support from magnetic fields or turbulent motions. Magnetic fields threading through the cloud exert a pressure that resists collapse along directions perpendicular to the field, though gas can still flow and accumulate along the field lines. This interaction between gravity, thermal pressure, and magnetic fields governs the rate and efficiency of star formation within dark clouds, producing the wide range of outcomes observed from isolated star formation in small globules to the clustered simultaneous formation of thousands of stars in giant molecular cloud complexes. Visibility in dark nebulae depends entirely on context. A dark cloud floating against the general diffuse light of empty space would be invisible. You would simply not see it. It becomes visible only when positioned against a brighter background, a region of emission nebulosity, a dense star field, a stretch of the glowing Milky Way background. And this means that the dark nebulae we have catalogued and named and studied are necessarily a biased sample. They are the ones that happen to be positioned against backgrounds bright enough to make their opacity apparent. The dark clouds that lie in front of similarly dark backgrounds are invisible to optical observation and detectable only through radio and infrared observations that reveal the molecular material directly, regardless of what lies behind it. There is a gentleness particular to a reflection nebula. It does not generate its own light. It does not burn, does not ionize, does not heat the gas around it to glowing temperatures. It simply sits in the vicinity of a star whose light it catches and scatters, and through that scattering it becomes softly visible, a borrowed glow, a gentle luminosity that belongs more to the star than to the cloud itself. Reflection nebulae are nebulae at their most passive, their most atmospheric, their most haze-like. If emission nebulae are the loud, warm, active members of the nebula family, the ones glowing with their own generated light, announcing the presence of hot young stars and ionized gas, then reflection nebulae are their quieter counterparts, present but not insistent, visible only because the geometry of their position happens to place them near enough to a source of light to catch some of it and send a portion of it in our direction. There is something worth sitting with in that quality of passivity. The reflection nebula is not doing anything in the energetic sense that a stellar nursery or a supernova remnant is doing something. No stars are forming within it. No shockwaves are propagating through it. No ultraviolet radiation is stripping electrons from atoms and causing them to glow. The dust is simply there, in the path of light that originates elsewhere, and the interaction between that light and those dust grains produces, almost incidentally, one of the softest and most atmospheric of all nebula types. The beauty of a reflection nebula is genuinely passive. It arrives without effort, without drama, as a side effect of proximity. The physics of the reflection is the same physics that makes a fog bank glow in the presence of distant lights. Dust grains scatter light at all angles, but they scatter short wavelengths blue light more efficiently than long ones. This preferential scattering means that the reflected component of starlight, as seen in a reflection nebula, is enriched in blue relative to the original starlight. A star that appears yellow or white will illuminate a reflection nebula with a distinctly blue glow. The dust is not changing the star's color arbitrarily, it is sorting the light by wavelength, directing the blue photons in many directions while allowing the red ones to pass through more directly. The red light continues on its original path, relatively undeflected. The blue light is scattered, redistributed across a wide range of angles, some of it toward us, giving the cloud its characteristic cool luminosity. This is the same principle that makes the daytime sky on Earth appear blue. The molecules of the atmosphere scatter short wavelengths more efficiently than long ones, directing blue light from the sun in all directions, while allowing the redder wavelengths to pass through more directly. A clear sky is, in this sense, a very diffuse reflection nebula, a scattering medium illuminated by a nearby star, redistributing the blue component of that star's light across the dome overhead. The physics operating in a reflection nebula 500 light-years away is the same physics operating in the few kilometers of atmosphere above you right now. The scale is different. The medium is different dust grains rather than gas molecules. But the underlying process, the preferential scattering of short wavelengths, is identical. The most famous example of a reflection nebula, or more precisely, a star cluster surrounded by a reflection nebula, is the Pleiades. The bright blue stars of this cluster, visible to the naked eye in Taurus as a small, hazy grouping, are presently passing through a region of interstellar dust. The dust is not a remnant of the gas cloud from which the Pleiades stars formed the cluster, has long since dispersed most of that material, its radiation and stellar winds having pushed the birth cloud away over the millions of years since the stars ignited. The current nebulosity is an independent cloud of dust that happens to lie in the cluster's path, illuminated by the stars as they move through it. The blue wisps and streamers visible around the brighter Pleiades stars in long exposure images are this unrelated dust, temporarily close enough to the hot blue stars to glow. The word temporarily is doing real work in that description. The Pleiades cluster is moving through this dust cloud at a speed that, by everyday standards, is enormous tens of kilometers per second relative to the surrounding medium. And yet the cloud is large enough, and the crossing time long enough, that the arrangement will persist for hundreds of thousands of years before the cluster emerges on the other side. From any human vantage point, the Pleiades will always be surrounded by their soft blue nebulosity. The arrangement feels permanent because the timescale of its change is so far beyond anything we can experience. But it is temporary, a coincidence of position, a chance alignment of a moving cluster, and an unrelated cloud of dust that happened to occupy the same region of space at the same time in galactic history. In a few 100,000 years, the cluster will have moved past this cloud, and the reflection nebula will fade as the illuminating stars recede, and the dust will continue drifting on its own separate path through the galaxy, dark again, invisible again, waiting for the next chance alignment. Hubble's variable nebula, associated with a young star in Monoceros, shows a different and more dynamic aspect of reflection nebulae. The nebula changes in shape and brightness over months, a timescale short enough that careful observers have been able to document and track the changes across the years since the nebula was first photographed in detail. The variations arise not from changes in the central star itself, but from shadows cast by dense, irregular concentrations of dust orbiting near the star. As these dense clumps move through the inner disk surrounding the young star, they block different portions of the star's light, causing shadows to sweep across the outer nebula like the hands of a very slow clock. The result is a reflection nebula that appears to shift and flicker on timescales accessible to human observation, a real-time shadow play driven by the motion of unseen objects in the inner regions of a young stellar system. There is something almost intimate about a nebula that changes on a human timescale. Most of what we observe in the night sky is, for practical purposes, static. The changes are real, but too slow to perceive across any individual lifetime, or even across the full span of recorded human history. Hubble's variable nebula is an exception, a place where the geometry of shadows and light plays out quickly enough that a person who photographs it in 1 year, and again the next, will see a measurably different object. The nebula is not different in its composition or its physics. The dust and the young star are doing exactly what dust and young stars do. But the particular arrangement of shadows at any given moment is unique, and that arrangement shifts month by month as the unseen clumps of dust in the inner disk complete their slow orbits around the central star. The Iris Nebula, in the constellation Cepheus, is a large and particularly beautiful example of a reflection nebula, a cloud of dust illuminated from within by a bright, hot star. The interplay of illuminated and shadowed regions in the iris gives it a complex, three-dimensional appearance, as if the dust cloud has real depth and structure, which of course it does. The blue glow of the illuminated outer portions contrasts with darker regions where the dust is thick enough to self-shadow, preventing the inner illumination from reaching the outer surface. The effect is the impression of a nebula with an interior, an enclosed space within the cloud, lit from within, its boundaries defined not by any physical wall, but simply by the distribution of the dust and the direction from which the light arrives. The iris looks, in long exposure images, almost like something you could step inside a cavern of soft blue light, its edges dissolving into the surrounding darkness, its interior warm with the glow of the star at its center. Reflection nebulae often occur alongside emission nebulae in the same general regions of space, because the conditions that produce one often produce conditions favorable for the other. A hot young star will ionize the nearest gas and create an emission nebula in the ionized region immediately surrounding it, while simultaneously illuminating more distant dust clouds with its visible light and creating a reflection nebula in the regions beyond the ionized zone. The transition between the two types is not always sharp. There are regions where emission and reflection blend into each other, where the gas is partially ionized and the dust is partially scattering, where the warm red of hydrogen emission and the cool blue of scattered starlight overlap in a single field of view. The Trifid Nebula is one example of this combination, a single object showing emission, reflection, and dark absorption characteristics, all within the same structure, each region governed by the particular balance of illumination, density, and dust content that happens to prevail there. The temporary nature of a reflection nebula is worth considering as you let this image settle. The star's light is constant, but the dust configuration is not. Dust clouds drift through space at the typical speeds of the interstellar medium, tens to hundreds of kilometers per second, relative to the stars around them. Over thousands of years, the alignment between a star and a particular dust cloud will shift. The dust that currently illuminates as a blue haze around a particular star will eventually drift away, and new dust may drift into position, and a different reflection nebula will form around the same star, with a different shape and different structure, for a different span of cosmically brief time. The reflection nebula visible today around a given star is a product of the current moment in a slow dance of relative motions, a temporary coincidence of position that makes the dust visible for a while, softly and without urgency, before the geometry changes and the glow fades and the dust moves on, dark and quiet, into whatever comes next. Everything that has been described so far, the star-forming nurseries, the emission nebulae, the dying stars with their expanding shells, the supernova remnants, the dark molecular clouds, the reflection nebulae. All of these are phases of a single, continuous cycle. They are not separate phenomena. They are not a collection of unrelated objects that happen to share a region of sky or a chapter in a book. They are different moments in the same long story that the galaxy has been telling and retelling for billions of years. The same atoms appear in each phase. The same forces operate throughout. What changes is only the arrangement, the density, the temperature, the degree of illumination, the particular form that matter is taking at this particular moment in its very long journey through the galaxy. It is worth pausing on that word, journey. It is not a metaphor, exactly. The material in a molecular cloud is genuinely in transit. It arrived there from somewhere else, from the dispersed remnants of earlier stars, carried outward by stellar winds and supernova shockwaves and the slow, turbulent stirring of the interstellar medium. And it will leave for somewhere else again, eventually, in the form of new stars and the nebulae those stars will produce when they die. The cloud is not a destination. It is a waypoint. A temporary gathering of material that has been moving through the galaxy for longer than the Earth has existed and will continue moving long after the Sun has exhausted its fuel. The story begins with a molecular cloud, a cold, dark, diffuse accumulation of gas and dust floating in the interstellar medium. Gravity slowly gathers this material, condensing it over millions of years into an increasingly dense structure. Within the densest regions of the cloud, fragmentation occurs. The cloud breaks into many smaller pieces, each one collapsing independently. Each collapsing fragment heats as it falls inward, the gravitational potential energy converting to thermal energy in the accumulating core. Eventually, after hundreds of thousands of years of infall, the core becomes hot enough and dense enough that hydrogen fusion ignites. A star is born. That ignition is not a sudden event. There is no single moment at which a protostar becomes a star, the way there is no single moment at which a child becomes an adult. It is a gradual crossing of a threshold, a slow brightening of the core, a slow increase in temperature and pressure, a slow awakening of the nuclear reactions that will sustain the object for millions or billions of years. The transition from collapsing cloud fragment to burning star takes hundreds of thousands of years, and the star that results is not fully itself. Immediately, it is surrounded by the disk of gas and dust from which it formed, still accreting material, still adjusting to the conditions of its new existence, still embedded in the parent cloud that gave rise to it. A star is not born complete. It arrives gradually, the way most things arrive. The new star, or more typically, the new cluster of stars, begins to irradiate the surrounding cloud. Ultraviolet radiation from the hottest and most massive stars ionizes the nearby gas. Stellar winds push outward against the cloud. The pressure of the radiation and wind carves cavities in the cloud, illuminating the inner walls as emission nebulae, compressing the outer regions and potentially triggering new rounds of star formation there. The parent cloud, which began as a dark, invisible structure, becomes a glowing, luminous, active region. The kind of stellar nursery we have been describing throughout this evening. The darkness becomes light. The potential becomes activation. The invisible becomes one of the most visually extraordinary objects in the galaxy. This transformation from dark cloud to glowing nursery is one of the most complete reversals in nature. The same material that was, a few million years ago, among the coldest and darkest things in the observable universe is now among the most luminous. The gas that was invisible, detectable only through radio telescopes sensitive to the faint emission of cold molecules, is now pouring out light at wavelengths across the entire spectrum: visible, infrared, ultraviolet, X-ray. The dust that was absorbing and blocking starlight is now being heated by the stars it helped create, and re-emitting that energy as infrared radiation, detectable across thousands of light years. The cloud has not been replaced. It has been transformed by the stars it made into something almost unrecognizably different from what it was before. Over millions of years, the most massive stars in the new cluster consume their fuel. They are profligate with it. A star 20 times the mass of the Sun burns through its nuclear fuel in only a few million years, a tiny fraction of the Sun's expected 10 billion-year lifespan. The very quality that makes these stars so luminous, so dominant, so visually spectacular, their enormous mass, is precisely what ensures their brevity. They cannot be both brilliant and enduring. The energy output required to support a star of that mass against gravitational collapse demands a rate of fuel consumption that exhausts the available supply in what is, by stellar standards, almost no time at all. They burn fast, and they end early, and their ending is as dramatic as their living. When the fuel is exhausted, the massive star's core collapses, and the outer layers are expelled in a supernova. The ejected material, enriched with the heavy elements synthesized during the star's life, expands outward as a supernova remnant, a glowing, X-ray bright, filamentary shell that will expand for hundreds of thousands of years. The blast wave from the supernova sweeps up interstellar gas, compressing it, heating it, potentially triggering new condensations and new star formation in neighboring regions of the cloud. The death of one massive star may, in this way, be the birth of others. The shock wave that disperses one part of the parent cloud may simultaneously compress another part to the threshold of collapse. Destruction and creation operating through the same mechanism, in the same moment, in the same region of space. The less massive stars in the cluster live far longer. Stars like the Sun burn quietly for billions of years before exhausting their central fuel and evolving into red giants. As they age, they begin returning material to the interstellar medium through stellar winds, and eventually through the slow mass loss of the red giant phase. There is no drama in this return, no explosion, no shockwave, no sudden release of energy. Just a slow, continuous outward drift of material from a star whose outer layers have grown large and loosely bound and susceptible to the gentle pressure of radiation. Over millions of years, a significant fraction of the star's total mass is returned to the surrounding space in this quiet, unhurried way, long before the planetary nebula phase that marks the final and most visible stage of the return. The planetary nebulae, they produce glow for tens of thousands of years, their material mixing gradually back into the interstellar medium. The white dwarf remnants, cool, dense, slowly fading, will persist for longer than the current age of the universe before they dim to complete darkness. And the material release the carbon, the nitrogen, the oxygen, the various heavier elements dredged up from the stellar interior by the convective mixing of the red giant phase, drifts outward into the surrounding space, enriching whatever molecular cloud material it eventually encounters, adding to the chemical complexity of the interstellar medium, one stellar death at a time. The interstellar medium, receiving all this returned material from stellar deaths, becomes gradually more chemically complex. Early in the universe's history, only hydrogen and helium existed. The first stars formed from this primordial gas lived brief lives and died, and in dying, they produced the first heavy elements and scattered them into the surrounding space. Each subsequent generation of stars formed from a richer interstellar medium, incorporated more heavy elements into their structure and into their planetary systems, and returned even more complex material when they died. The galaxy has been running this recycling program for billions of years, and the result is an interstellar medium that now contains trace quantities of virtually every element in the periodic table, distributed through the gas and dust of molecular clouds, waiting to be incorporated into the next generation of stars and worlds. Each cycle leaves the medium slightly more complex than it found it. The first generation of stars enriched the primordial hydrogen and helium with the first traces of carbon, oxygen, and other elements produced in stellar interiors. The second generation formed from that slightly enriched medium, produced more heavy elements, and returned them at death. And so on, through many generations, each one building on what the previous ones left behind, not in any directed or intentional way, but simply as a consequence of the physics of stellar nucleosynthesis and the dispersal of stellar material at death. The galaxy accumulates complexity the way a river accumulates sediment, not by trying to, not by any design, but simply because the conditions are right and the time is long. This enrichment is what makes rocky planets possible. The first generation of stars formed from nearly pure hydrogen and helium could not have supported the formation of rocky planets like Earth. There was simply not enough silicon, iron, oxygen, and other rock-forming elements in the available gas. A planet requires ingredients that primordial nucleosynthesis did not produce in significant quantities. It requires the output of stellar interiors, the carbon and oxygen made in helium-burning stars, the silicon and sulfur and calcium made in the later stages of massive star evolution, the iron and nickel produced in the cores of the most massive stars and dispersed by supernova explosions. All of these had to be made, scattered, mixed into the interstellar medium, and gathered into a new molecular cloud before a planetary system like ours could form. By the time the solar system formed, the interstellar medium had already been enriched by many previous generations of stars, enough that the disk of gas and dust surrounding the young sun contained sufficient quantities of heavy elements to condense into the rocky bodies we call the terrestrial planets. The solar system formed from ancient nebula material, from a molecular cloud that was itself assembled from the dispersed remnants of stars that lived and died before our sun existed. The Earth is, in the most literal possible sense, made of recycled stellar material. Not metaphorically, not approximately. The atoms in the rock and the ocean and the air and every living thing on this planet were processed through stellar interiors before they arrived here. It is possible to trace the cycle in both directions from any given point. Looking backward, the atoms in a rocky planet arrived via the dispersed remnants of earlier stars, which formed from molecular clouds, which assembled from the dispersed remnants of even earlier stars, back and back toward the earliest, simplest material of the universe. The chain is unbroken. Every atom has a history that extends further back than the solar system, further back than the Milky Way as it currently exists, back toward the first few minutes of cosmic time, when the simplest elements were forged in conditions of almost unimaginable heat and density. Looking forward, the gas and dust currently in molecular clouds will form new stars and planetary systems, some of which will develop in ways that lead to further complexity, and eventually those stars will return their material to the cycle, enriched further. The galaxy is not running down. It is rearranging. There is something quietly extraordinary about the carbon atom, which is found in every living thing on Earth. Carbon is not a product of primordial nucleosynthesis. the first few minutes of the universe produced only hydrogen and helium in significant quantities. Carbon forms inside stars through the nuclear fusion of helium nuclei in stellar interiors, a process that requires the conditions found only in the cores of aging stars, temperatures and pressures that do not exist anywhere else in nature. When stars die and return their material to the interstellar medium, whether through planetary nebulae or supernova explosions, that carbon is released. It drifts in the interstellar medium, possibly incorporated into dust grains, eventually swept into molecular clouds, eventually condensed into protoplanetary disks, eventually gathered into planetesimals and planets, eventually, in some cases, incorporated into biological molecules. The carbon atom in an organic molecule on Earth has likely cycled through at least one stellar interior before arriving here. Possibly more than one. It is ancient material, shaped by conditions we can barely simulate in laboratories, on a journey that began before the Sun existed and will not end when the Sun eventually does. The galactic cycle also has an enormous spatial scale. The material in the interstellar medium does not stay in one place. Stellar winds, supernova explosions, the turbulence driven by all these energetic events, these stir the interstellar medium on scales of hundreds of light-years, distributing material broadly through the galactic disk. An element synthesized in a massive star in one part of the galaxy might, over billions of years and multiple cycles of stellar birth and death, end up in a very different part of the galaxy, entirely carried outward by successive supernova shockwaves, swept into different molecular clouds, incorporated into different stars, expelled again at death, and carried further still. The galaxy mixes its material gradually, homogenizing its chemical composition over vast timescales, sharing the products of stellar nucleosynthesis across distances that no individual atom traverses quickly, but that the cumulative effect of many cycles crosses easily. Different regions of the galaxy are at different stages of chemical enrichment, but the overall trend, everywhere, is toward increasing complexity. The emission, dark, reflection, planetary, and supernova nebulae we have visited tonight are not separate chapters, but the same chapter, told from different perspectives and at different moments. The dark molecular cloud is the potential, the quiet gathering of material in the cold, the invisible accumulation of the ingredients from which everything else will come. The stellar nursery is the activation, the moment when gravity has won enough of its long argument with pressure that collapse becomes inevitable and stars begin to emerge. The emission nebula is the announcement of birth, the illumination of the surrounding gas by the energy of the newly formed stars, the transformation of darkness into light. The planetary nebula is the gentle return, the slow, quiet exhalation of a sun-like star's outer layers, the dispersal of enriched material back into the medium from which it came. The supernova remnant is the energetic return, the violent, X-ray bright dispersal of a massive star's enriched interior across hundreds of light-years of surrounding space. The reflection nebula is the quiet illumination of what remains the borrowed glow of dust that has not yet been swept up into anything, illuminated by the nearby light of stars it did not make and cannot absorb. They are all the same material, the same atoms, cycling through phases cloud, star, nebula. Cloud with a patience that makes the word patient seem almost inadequate. The cycle does not hurry. It does not have a destination. It simply continues, as it has continued for billions of years, redistributing matter and energy through the galaxy in ways that gradually, cumulatively, quietly build more complexity than existed before. And somewhere in that cycle, in the particular arrangement of enriched material that happened to be available in one particular outer spiral arm of one particular galaxy at one particular moment in cosmic history, the present, Conditions were right for a rocky planet to form, and for that planet to develop the chemistry of life, and for that life to eventually develop the capacity to look back up at the clouds from which it came and recognize, with whatever sense of recognition is available to it, the material it is made of. Everything has a lifespan, even the structures and conditions that feel most permanent from a human perspective. The stellar nurseries that now glow so brightly across the Milky Way are not permanent features of the galaxy. They are temporary localized concentrations of activity in a medium that will eventually quiet as the available supply of molecular gas is gradually consumed or dispersed. This is not a melancholy fact. It is simply the nature of the cycle, the same cycle that produced the nurseries in the first place, that has been producing and dissolving them for billions of years, that will continue to produce and dissolve them long after the ones we can observe tonight have faded back into the general diffuse medium from which they came. The Orion Nebula, which has been forming stars for perhaps a few million years already, will not continue to do so indefinitely. The most massive and luminous stars forming within it will live only a few million more years before expiring in supernovae. Their deaths will release energy that further erodes and disperses the remaining molecular gas of the parent cloud. The ultraviolet radiation already pouring from the young massive stars in the trapezium cluster is progressively ionizing and evaporating the surrounding material, eating away at the molecular reservoir that feeds future star formation. Over the next few million years, a brief interval in galactic history, the Orion Nebula as a glowing structure will fade. The gas will disperse into the broader interstellar medium. The young star cluster that formed within it will drift away, its stars scattering gradually as their mutual gravitational attraction weakens over time. The nebula itself, as a distinct, luminous entity, will cease to be. It is worth sitting with that for a moment, not with sadness, but with a kind of gentle attention. The Orion Nebula that we can observe tonight, that has been visible to human eyes for as long as human eyes have turned toward that part of the sky, is a temporary arrangement. The light that makes it visible is the same light that is, slowly and continuously, destroying the conditions that produce it. The stars illuminate the nebula, and in illuminating it, ionize and evaporate it. The brightness is the dissolution. The glow is the goodbye. And yet the time scale of that goodbye is so long, millions of years, that it qualifies, from any human vantage point, as permanence. The Orion Nebula will be there tomorrow night. It will be there for every human lifetime that will ever be lived on this planet. Its impermanence is entirely theoretical, entirely beyond the reach of experience. This is not unusual. Every stellar nursery has this trajectory, a finite period of activity bounded by the consumption or dispersal of the molecular material that sustains it. The molecular cloud complexes along the Milky Way's spiral arms are being gradually depleted, their material converted into stars, returned to the interstellar medium in a less dense, less molecular form, and spread too diffusely to immediately reform into new molecular clouds. The galaxy's star formation rate is thought to have been considerably higher in the distant past, when more molecular gas was available. It has been declining slowly over billions of years, and will continue to decline as the gas supply shrinks. The Milky Way was once more active, more luminous in its star-forming regions, more filled with the blue-white light of young massive stars burning through their fuel with the brief extravagance characteristic of the very massive. That era is not over, but it is past its peak, and the decline, though slow beyond any useful comprehension, is real. On very long timescales, billions of years from now, the Milky Way will be a quieter place. Most of the gas currently available for star formation will have been converted into stars or diffused into a form too hot or too dispersed to collapse. The stellar population will shift toward older, cooler, dimmer stars. The brilliant blue supergiant stars that currently dominate the light of young star clusters will all have long since ended. The galaxy will be populated predominantly by long-lived stars of modest mass stars like the Sun, or smaller burning slowly and quietly, their stellar nurseries long since gone dark. It will be, in a sense, an older galaxy, not dying, not dead, but settled into a calmer phase, the way a fire settles from active flame into steady, patient coals. Still warm, still present, still doing the work of being a galaxy, but quieter and less given to the dramatic brightness of its younger years. The sky of that future galaxy, seen from a planet like this one, would look different from the sky visible tonight. The great glowing patches of emission nebulosity that mark the spiral arms, the Orion Nebula, the Carina Nebula, the Lagoon, the Eagle, would be gone, or so faded as to be unrecognizable. The star clusters that formed within them would have long since dispersed, their stars scattered across the galactic disk, indistinguishable from the general stellar population. The sky would be rich with stars, but they would be the quieter stars, yellow and orange and red, the long-lived ones, burning patiently through fuel reserves that will last for billions of years yet. It would be a gentler sky, a more uniform one, still beautiful in its own unhurried way, but differently beautiful, the beauty of age rather than the beauty of youth. Planetary nebulae will continue to appear for a long time after the great stellar nurseries have quieted. Every sun-like star will eventually evolve off the main sequence, swell into a red giant, shed its outer layers, and leave a glowing shell. Since sun-like stars live for billions of years, there will be planetary nebulae forming in the galaxy long after the last stellar nursery has faded. They will be the final flourish of an aging stellar population. Gentle, quiet, geometrically complex shells of gas glowing around small white dwarf cores, illuminated not by the fierce radiation of massive young stars, but by the slower, cooler radiation of dying suns. The planetary nebulae of that distant future will be the last sustained light show the galaxy produces, soft, slow, short-lived by astronomical standards, but continuous. As generation after generation of aging sun-like stars reaches the end of its long, quiet life and exhales its outer layers into the surrounding space. There is something worth noticing in that image, the idea of a galaxy in which the only active nebulae are planetary nebulae. Soft shells of expelled stellar atmosphere glowing briefly around their cooling remnant cores. No great nurseries blazing with the birth of thousands of stars simultaneously. No supernova remnants expanding at enormous speeds, seeding the interstellar medium with freshly synthesized heavy elements. Just the quiet, individual farewells of stars that have lived their full, long lives, each one a small, temporary, geometrically intricate glow in the dark, present for a few tens of thousands of years before fading back into the thinning interstellar medium. It is, in its own way, a peaceful image. A galaxy winding down slowly, not in catastrophe, but in the quiet completion of very long individual stories. The white dwarfs themselves persist. They cool very slowly. The timescale for a white dwarf to cool from a hot, luminous remnant to a cold, dark object is estimated to be longer than the current age of the universe. No white dwarf has yet had time to cool completely. The galaxy contains hundreds of billions of white dwarfs in various stages of cooling, most of them invisible cold embers distributed throughout the disk, carrying within their dense interiors the compressed remnants of stellar interiors, the processed ashes of nuclear burning. They are not nothing. They are extraordinarily dense, A teaspoon of white dwarf material would outweigh a small car. They are the most compressed, stable form of matter that ordinary stellar physics produces, short of the neutron stars left behind by far more massive stars. They hold within them the record of everything that star fused and processed across its long hydrogen-burning life. And they cool, slowly, over timescales that exceed anything in our experience of how long things take. Eventually, on timescales far beyond anything relevant to human experience, the last of these remnants will cool to darkness. What had been a hot, luminous white dwarf will become a black dwarf, a cold, dark, inert ball of compressed matter, no longer emitting any meaningful radiation, drifting silently through the galactic disk in the dark. No black dwarfs exist yet. The universe is not old enough for any white dwarf to have cooled that far. Every white dwarf currently in the Milky Way is still warm, still faintly luminous by the standards of what they will eventually become, still radiating the last warmth of their stellar lives into the surrounding dark. The galaxy is still, in this sense, lit from within by ancient embers. And the galaxy will be quieter still when the last of them finally dims. The interstellar medium that remains gas that was never incorporated into stars, or that was returned from stellar deaths in too diffuse a form to collapse again, will slowly settle into a thin, cool, quiescent state. The turbulence, driven by stellar energy input, will gradually damp as the sources of that energy fade. The medium will become calmer, more uniform, less structured. The rich chemistry of molecular clouds, sustained by the cycling of material through stellar interiors and back into the gas phase, will slowly become impoverished as fewer and fewer stars are born and die to enrich it further. The complex organic molecules found in cold molecular clouds today depend ultimately on the heavy elements produced by stellar nucleosynthesis. As the cycling slows, the chemical richness of the interstellar medium will stagnate. The long conversation between matter and energy that has been building complexity for billions of years will begin, very slowly, to fall quiet. None of this is imminent. The Milky Way is not at the end of its star-forming life. It is in middle age, its most prodigious era of star formation already past, but still actively forming stars at a rate of several per year. The molecular clouds that are present today will sustain star formation for hundreds of millions to billions of years yet. The galaxy still has a long, active future ahead of it, even if that future is quieter than its past. And over those billions of years, the great recycling continues, clouds to stars, to nebulae to clouds, slightly enriched with each cycle, the medium becoming slowly more complex, the possibility space of chemistry and structure gradually expanding. The galaxy is not winding down tonight. It is simply, as it has always been, in the middle of a very long process that has no urgency and no deadline and no awareness of its own direction. There is a kind of peace in thinking about this long future. The universe does not rush toward any endpoint. It slows, it cools, it spreads, but it does so over timescales so immense that from any individual vantage point, the change is imperceptible. The sky visible tonight will look essentially the same to observers a million years from now. The stars in the Orion constellation will have shifted slightly in their positions. The nebula may be a little dimmer, but the overall scene will be recognizably continuous with what exists tonight. The pace of change is so slow that it qualifies, for all practical purposes, as stillness. Stillness is, in fact, a useful frame. Not because nothing is happening, everything is happening, all the time, at scales from the quantum to the cosmic. But the pace of galactic transformation is so far removed from human timescales that it presents to any individual consciousness as a kind of profound calm. The gas clouds drifting between the stars the slow collapse of molecular cores, the gradual expansion of planetary nebula shells, these are all in motion, all evolving, all part of the ongoing transformation of the galaxy. But from where you lie tonight, on a planet orbiting a middle-aged star in an outer spiral arm, the sky is still. The stars are still. The nebulae are still. The light arriving from them has been traveling for centuries or millennia, and it arrives now, in this moment, quietly. And you can receive it quietly, and let it be enough, and rest. The gas and dust between the stars never rests, but it does move slowly, so slowly that over the span of any individual life, it appears to do nothing at all. The nebulae we have visited tonight are still out there now, in the same regions of sky where they have been for thousands of years, continuing their quiet processes without urgency, without audience, without awareness of being observed. The pillars in the Eagle Nebula are still eroding. The shells of planetary nebulae are still expanding. The shockwaves of supernova remnants are still spreading through the interstellar medium. The cold cores inside dark molecular clouds are still slowly gathering themselves toward collapse. And the light from all of these structures is still traveling outward in all directions, including toward this small planet, arriving continuously at the receivers we have pointed toward the sky. Every photon in a nebula image represents a small event, an electron recombining with a proton, a dust grain scattering a wavelength, a magnetic field directing a charged particle. Each one is a tiny message about conditions somewhere in the galaxy, conditions that existed decades or centuries or millennia before the photon began its journey. The sky is full of these messages, arriving without pause. You can let all of this continue without you for a while. The gas and dust will drift, whether you are watching or not. The stars will slowly form and burn and die on their own long schedules. The galaxy will continue its patient rearrangement of matter across timescales that dwarf anything the mind can really hold. And somewhere inside that enormity, in a quiet outer arm of an ordinary spiral galaxy, you are still, and the day is behind you, and the night is soft and undemanding. There is a particular quality to the stillness that settles over a topic like this one at the end of a long evening of listening. You have moved, in some sense, through enormous distances tonight, through the warm, glowing nurseries of Orion and Carina, through the delicate geometric shells of planetary nebulae, through the ancient filamentary remnants of stars that ended long before our own sun had finished forming. You have passed through regions of gas so cold they approach the lowest temperature that physics permits, and through plasma so hot it radiates in wavelengths far beyond anything the eye can detect. You have, in a sense, been very far away, and yet you have not moved at all. You are exactly where you were when the evening began, settled, quiet, the weight of the day slowly releasing from the parts of you that have been holding it. The distances were real. The physics was real. But the traveling was effortless, the way listening always is, and the return is just as easy. There is nowhere to come back from. There is only here, which was always here, which is soft and still and adequate in every way. The Orion Nebula is 1,300 light-years away, and it is doing exactly what it was doing when you first began to listen. The trapezium stars at its center are still pouring ultraviolet radiation into the surrounding gas. The protoplanetary disks around young stars in that cloud are still spinning, still slowly gathering material, still in the long, patient process of deciding what kind of planetary systems they will become. The horsehead is still rising from its glowing background, its shape still being slowly carved by stellar winds, its dense interior still cold and dark and shielded from the radiation pressing at its outer edges. None of it has changed in any way that would be measurable across the span of a single human night. This is one of the quiet gifts of thinking about the sky at this scale. Nothing that has been described tonight is fragile in the way the events of a human day are fragile. Nothing can be undone by tomorrow. Nothing requires your attention to continue. The molecular cloud that will, in 3 million years, become a new star cluster is already in the slow, early stages of its collapse, and it will reach that outcome regardless of whether anyone on this planet is awake or asleep or even present to observe it. The universe is not waiting for input. It is simply proceeding, as it has always proceeded, with a patience that makes the word patience seem almost insufficient. You might find something restful in that thought if you let it settle gently. The great work of the galaxy, the cycling of matter, from cloud to star, to nebula to cloud, the slow enrichment of the interstellar medium, the gradual building of chemical complexity across billions of years, all of that is underway tonight, and has been underway for longer than the Earth has existed, and will continue long after everything we consider permanent has changed beyond recognition. And none of it requires anything from you right now. Not attention, not effort, not even awareness. It will proceed in the dark, in the silence, whether you are conscious of it or not. The light from a nebula 500 light-years away has been traveling toward this planet since before most of the buildings in the oldest cities on Earth were built. It crossed that entire distance, photon by quiet photon, navigating the thin gas and occasional dust of the interstellar medium, curving slightly around the gravity of stars it passed near, and arrived here, at this atmosphere, at these telescopes and detectors and eyes, at this moment without any urgency at all. The photon did not know it was arriving. It had no awareness of the destination. It simply traveled at the speed light travels, through the medium that was there, for as long as the journey required. And when it arrived, it delivered its small message about the conditions it left behind, the temperature, the density, the atomic species, and was absorbed and was done. Every image ever taken of a nebula is made of arrivals like that. Millions of photons, each one a traveler from a different point in the cloud, each one carrying information about a slightly different piece of the structure, each one having made its own long, quiet crossing from source to detector. The image that results is a kind of accumulated listening, a record of light that chose, by geometry, to travel in our direction, gathered over minutes or hours of exposure into something the eye can hold. And the cloud that sent those photons is still sending them. The same processes that produce the light in any given image are still producing light right now. And that light is on its way, and it will arrive, and it will be received, long after anyone who looked at the original image has gone. The Veil Nebula, in Cygnus, that long, flowing curtain of cooling gas that marks the edge of a supernova remnant thousands of years old, is still emitting. Its filaments are still cooling, still organizing themselves into the soft wisps and sheets that make it so visually distinctive. The light from those filaments that will arrive at Earth 100 years from now is already traveling. It left the nebula 100 years ago, minus however long the crossing takes, and it is on its way, indifferently crossing the dark, carrying its message about the state of a piece of cooling plasma on the edge of an ancient explosion. The sky is full of light, already in transit. The messages already sent are beyond counting. You are lying at the bottom of an atmosphere on a small, warm, unremarkable planet, and the universe is sending you messages continuously, and most of them will never be received, and none of that matters at all, and the night is very soft. The white dwarfs scattered throughout the Milky Way, the cooling remnants of stars like the Sun, compressed into objects the size of Earth and slowly radiating the last of their stored heat into the long dark, are cooling tonight as they cool every night, and every night before this one, and every night to come. The timescale on which a white dwarf cools is longer than the current age of the universe. None of the white dwarfs that exist have yet cooled to darkness. They are all still warm, all still faintly luminous, all somewhere in the early stages of a process that will not finish for longer than anything we can usefully imagine. There is something almost companionable in that, if you let yourself feel it. The remnants of ancient stars are still warm. The universe has not yet gone cold. There is still light in the old places. And somewhere in the molecular clouds of the Milky Way right now, in the cold, dark, dense cores of clouds that will not produce visible stars for another million years, hydrogen molecules are drifting fractionally closer to one another than they were an hour ago. The collapse is almost imperceptible. The change in density over any single night is far too small to measure. But the direction is set, and the outcome is determined, and very slowly, in the way that makes geological processes look sudden, a future star is drawing itself together out of the dark. The material that will become that star is, right now, the coldest matter in the observable universe. It is only a few degrees above absolute zero, the temperature at which all thermal motion ceases, the floor of temperature that physics defines as the lowest possible. And within that almost perfect cold, that almost complete stillness of molecular motion, something is happening anyway. Gravity does not require warmth. It does not require speed or energy or urgency. It acts quietly on whatever is present, regardless of the temperature, regardless of the time. It is the most patient of forces, and it is working tonight, as it works every night, in the cold, dark interiors of clouds that have no light of their own. The nebulae are still there. They will still be there tomorrow. There is nothing to hurry toward, and nothing you have missed. The sky remains quietly, continuously active, long after listening ends, and all of it will be here, unchanged in any way that matters, whenever you choose to return. You can rest now. The Orion Nebula does not need you awake. The Eagle Nebula's pillars will continue their slow erosion without witness. The Ring Nebula's shell will expand by a distance too small to measure between now and morning, and the white dwarf at its center will still be there, still faintly glowing, still radiating the last warmth of its long stellar life into the surrounding dark. None of it is hurrying. None of it is waiting. None of it will be any less present or any less extraordinary when you come back to it, rested, in the daylight, or in another quiet evening like this one. The gas and dust between the stars will drift as it always drifts. The light will travel as it always travels. The galaxy will continue its patient, unhurried rearrangement of matter and energy across distances and timescales so large they become, eventually, almost indistinguishable from peace. Sleep well and good night.